For in last lecture, we started discussing about CPU scheduling. In scheduling, we basically look at how the algorithms are used to allocate the processes to the CPU, and each process would actually follow through a life cycle, and that life cycle would have different phases of life: ready queue, then waiting, then running, and then interrupted and back to the ready queue. So as we discussed that it is the number of life phases or stop or life cycle. It depends upon the operating system and the hardware which is being used, but mostly each process, the phases which we have discussed is used for each and every operating system. So a process is added to the ready queue, and the short-term scheduler would actually create a queue for dispatcher, from where the dispatcher would actually pick the highest priority task and submit that to the CPU. So submitting a process to CPU means allocating the time of the CPU to that particular process. Now we discussed about first come first serve scheduling, in that which was non-preemptive scheduling. Non-preemptive scheduling means that if a process start running and it required the CPU, no other task in the ready queue can interrupt it, and it would actually complete its CPU burst, and then it will go to its IO state or whatever state or terminate. So that is basically non-preemptive. In preemptive scheduling, whenever there is a highest priority process is added to the ready queue, the lowest priority process, which is currently running on the CPU, would be interrupted and put back into the ready queue. So that is called preemptive scheduling. Now, both type of scheduling we use, preemptive and non-preemptive, because there's, as we know, that the computer science and the algorithms are never perfect for each type of job, and that's why not every algorithm is good for every type of process. Even some processes need to be non preemptive, and some are non-preemptive. So it is a mix of everything that would be used. Even we would be using these algorithm, which would be the mix of it. So we would also be using in the modern operating system. First come first serve is also used, round robin is also used, then shortest job first is also used. So there are variants of it, like how you are creating the priority and how you are putting one process ahead of other. If you remember, ready queue is basically a linked list. So the process which has highest priority would be at the head of that queue, and the process which is having lowest priority would be at the end of or the tail of the queue. So from that particular ready queue, the dispatcher would actually pick the jobs and allocate to the now. Before we proceed further on discussing other algorithms, I just wanted to share with you one command that is used to look at the historic events or what has happened to on your computer system and hardware or operating system, how it was managing. So to get the historic snapshot of few things like procs, memory, swap memory, IO, system, and CPU, vmstat is one command that you can use. So if I simply pass it without parameters, it will give me the recent one. It will give me the historic event till since my system is booted. So it will give me 1 second snapshot since my computer was booted. So this is, here you can see the number of the context switching. CS means the number of context switching that has performed historically on the system. And the other parameters which are there are, like, we go by procs, you know that it is about the processes. So R means the process which are basically the number of processes which are in waiting state. So this will actually tell us the number of the processes which are in waiting state. and then B is the number of processes which are blocked and in a sleep mode interrupted for your waiting for some IO to happen. Then in memory is a swap. Swap is the amount of virtual memory that is used. This we will be discussing in the next chapters. Then the free memory, the buffer space and the cache which has been used. So whereas in swap is the number of swap in from the disk and number of out to the disk. So anyone knows what is swap memory? Brandon, yeah. So normally we, whenever you actually install your Ubuntu or Linux system, we give an extra swap memory. So extra swap memory is basically used by your operating system when your RAM, the main memory is full. So the main memory, if it is full, then your operating system or your Linux system would start using that swap memory which is existing on a secondary storage. So we usually give the swap memory when we install operating system or Ubuntu system. So this is usually equal to the double of the RAM. So if your RAM is like 4 gigs, then the swap should be of 8 gigs. So this is basically the formula that is being used. But nowadays it may be possible that you can have a lower swap memory size. So this is used in case your RAM is full. Swap is that is basically to the PCB. So PCB is different. Then there is a heap memory. So from that it is allocated to each and every process. So this we are talking about the system level, not the process level. So IO is basically elaborating about the number of blocks per second received from a block of device, and this is BO is the number of blocks per second sent to a block device. We are more concerned here about system. In system we have in means the number of interrupts per second, and then CS is the number of context switching that has been performed. So this would actually tell you how fast your processes are basically switched to get the maximum utilization of your processor. And then the last is CPU. CPU would be actually saying you how much CPU is utilized for user processes, SI for system processes, ID for the idle, WA is for wait, and ST for steal the CPU cycle. So this would be used whenever like you all have installed virtual boxes. So it may be possible that your host and the guest are trying to get and access the same memory location, and then or resource. Then there is the host gets priority over the guest, and that would deteriorate the performance of your virtual box. And this particular consumption is shown like that how many times your CPU, your host CPU has stolen what was required for your virtual box. So this is an additional thing, but for us, I think US, SI, and ID. These are three main parameters to look at. Now you can look at my CPU is 99% free. So this brings in the concept of using distributed computing, and where we can actually connect this particular computer onto network and other processes which requires huge computation power. They can actually utilize my CPU cycles. So even if they are using 50% of my CPU cycle, even then I'm good, because my processes are just using 1% of my CPU. And this is how we can contribute. This is a concept of distributed computing. And even now there are some programs that they usually ask for your mobile device to contribute for remote processing. So that is just happening because we have free CPU cycles, and our own jobs are not requiring this. So this is all about that. Okay, so we can look at this is interval. Like I want 1 second snapshot, and how many snapshots I want. I want 10 snapshots. So the first line would be giving me the snapshot of the historic thing since my computer booted up, and all other are current snapshots. So what is happening right now? So this is happening the first second, then the second after that, then the third second. So this is basically showing me the number of interrupts and the number of context switches those have performed over 1 second interval. I could change this interval into 5 seconds, and I want 3 records, so it will be actually coming after 5 seconds. So it will give me the aggregated or average value for 5 seconds. So this is what is coming. Now here you can see that my CPU is 100% almost 100% free for last 10 seconds. So that's how basically we can look at different things. Now the top is one of the command that we have been discussing a lot. The same thing is happening here, but we have a snapshot how your processes are basically working and showcasing the utilization of your computer. Okay, now moving towards the next thing. This we have discussed. First come first serve has been discussed. Then we discussed about shortest job first, and then in shortest job first, the main thing is the prediction of the next CPU burst. So based on that, we can actually predict better and allocate the jobs better to the CPU. And now from today, for today, we are going to discuss about round robin and other algorithms. So round robin is one of the very favorite algorithms, which is creating a very responsive result, because in round robin, time slice is given to each and every process rather than just allocating one process to the CPU. So what happens, we assign a time quantum, so let us say t, and after t, each time quantum of t milliseconds, the context switching would happen. So if, let us suppose, we have 3 processes, p2, p1, p2, p3, then all are the priority is 1, 2, 3, and then p1 would actually start executing. After t milliseconds, the context switching would happen and p2 would start running, and then after another t milliseconds, context switching would happen and p3 would start running. So this is basically the time quantum which we gave. So the time quantum is the key, and this is an optimization parameter. Like, we have to fix how much time quantum is good for a particular type of operating system, for particular type of jobs, so that there are a minimum number of context switching happening. So if you remember, whenever we perform context switching, so there is called dispatch latency. This dispatch latency is a time taken by dispatcher to actually change the PCB from one state to from saving the state of one process which is currently running onto PCB, and then restoring the state of another process from the PCB, and so that it can execute. So that time is basically called dispatch latency. So whenever the context switching is happening, so there is an overhead of this dispatch latency onto operating system. So we usually try to have the time quantum which is good enough to cater the class of the processes. So round robin scheduling algorithm is similar to first come first serve scheduling, but preemption is added to enable system to switch between the processes. So each process would get a small CPU time quantum. Usually it is between 10 to 100 milliseconds, and after this time has elapsed, the process would be preempted and added to the end of the ready queue. So this is what happens to when we are using a round robin. Ready queue is treated as a circular queue because we are going on. So here it is P1, then P2, and so on. This is one time quantum, and each process would be switched after one time quantum, and timer interrupts every quantum schedule the next process. there are two things those could happen when we are basically performing context switching. One is that process was smaller than the CPU burst of that process was smaller. So let us suppose the quantum time Q is 6 milliseconds and the CPU burst of that particular process which we are hoping to be allocated is only 3 milliseconds. So if it is 3 milliseconds and the quantum size is 6 milliseconds, then what would happen is whenever it is allocated to CPU, before the time quantum comes, your process would already be executed or terminated or went for volunteer into wait state. So in that case, we are good and it is perfectly scheduling all the jobs. The process may have the CPU burst for less than one time quantum, and in this case the process itself releases the CPU voluntarily. So scheduler will then proceed to the next process in the ready queue. The second thing could happen is if it is 13 milliseconds and the time quantum is 6 milliseconds, then this particular process would require more than two contexts, more than two time quantums to actually run to its full execution time. So because this would be 13 and 6, so it'll be 2 plus 1 equal to 3 quantums would be requiring for this particular process to run if the CPU burst time is greater than the quantum time. So that is one thing is there. So RR scheduling is preemptive and performance if the queue is large. Q means time quantum is very large, then your algorithm would become FIFO, so first in, first out. And if it is small, then there is an overhead of context switching, which may be too high. So rule of thumb is that 80% of whenever we decide on Q, what is an optimal size of Q, we should decide that 80% of CPU burst should be shorter than the time quantum. So the CPU burst, basically the class of the program or the processes, those are running on the computer. So 80% of processes with the CPU CPU burst should be smaller than the quantum, then this would be this RR would be performing optimally. Very good. Now, if I say I have these three processes, P1, P2, P3, then how it will be actually executing. This all is available. All these processes are available at time 0 second, and it basically starts with the process P1. It runs over. Now here the quantum time is 4 millisecond. So here the time quantum is 4 millisecond. So P1 would run for 4 millisecond, then P2, then P3, then P1, P2, P3. So because what happens is the P1 and P2, P2 and P3 both are 3 milliseconds. So they will finish within one quantum time. And whereas others, this one would take a number of quantums to actually time slices to actually run to its end or terminate or wait for its state. So the average waiting time for P2 is 4 because it started after 4, and then for P3 it is 7 because it started at 7. Now for this, the total average waiting time for P1 is, because this was allocated already and then it again started at so the total waiting time for P1 was 10 minus 4, so it's 6. What would be the waiting time for the processes? So it will be something like for the process P2, which is the shortest job, and whenever there is like conflict, both are having a same CPU burst, then the first come first serve kind of thing would be happening. So let us suppose P2 would be running first, so waiting time for P2 would be 0. Then we have waiting time for P3 would be 3, and then for this would be for the P1 would be 3. So it will be 6 by 3 is equals to 2 milliseconds. As I discussed, that shortest job first algorithm is most optimal algorithm for scheduling, but round robin is good because it basically gives a better response. Why? The response time is the time every process would take to show for the first time. So here you can see every process would get a fair amount of time within like number of quantums to actually show out its first instance. Like P1 would start execution, it will start responding. Basically P2 would start responding, P3 would start responding. So a round robin basically makes and give the equal chances for all the jobs to respond. And this is why this is called a fair algorithm, because it just allocate the time slice for each and every process, and each and every process would be starting responding to and start its processing. Hope I'm clear on it. So but the round robin has higher average turnaround time than shortest job first, and but it is better on response. So if you remember what is turnaround time and why it is basically having higher average turnaround time, because it performs so much of context switching. So whenever we say there are number of context switchings are happening, every context switching would also take time, and turnaround time is the total complete completion of the process. So how much time a job would actually take for completion. So that is basically is higher for round robin as compared to shortest job first. So Q should be large enough as compared to context switching. Q should be usually in between 10 milliseconds to 100 milliseconds, and the context switching should be taking time less than 10 microseconds. So this is basically the benchmark which is used for setting right the quantum. And also the another thing that we have discussed is it depends upon the type of the processes those are running on your computer. 80% of CPU burst should be smaller than the size of the quantum, and then your round robin algorithm would give you optimal performance. So let's just another example. Here the process time is 10 and the quantum time is 12. Then the number of context switching happening is 0. Here the quantum time is 6. It means the two context switchings are happening. So CS1, CS2. So there's basically one context switching is happening, sorry, because there this is 6 and it would be divided. Now here if the context switching is quantum size is 1, so after every 1 millisecond the context switching would happen. So how many would be there? So it is 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 context switchings would be happening for that particular process, and it every context switching adds an overhead, whether it is running the same thing or the other process. So the turnaround time varies with the time of the quantum. So here is a graph which says that the longest process is 6. So it should be the 80% of the jobs should be smaller than basically the quantum time. So we can see at quantum size 6 millisecond, the average turnaround time is minimal. So this is the thumb rule that we have to follow for implementing the round robin algorithm. Okay, so now the priority scheduling. The priority scheduling is also something similar to shortest job first, because there we basically prioritize the processes based on the next CPU burst. But there are other parameters by which we can actually set the priorities of the processes. It may be internal or external. So there may be the time limits, the memory requirement, number of open files, the ratio of average IO burst to the average CPU burst. Those can be used as a parameter to set the priorities of the processes. So whereas there could be external priorities which are set based on the criteria outside of the operating system. Let us suppose there is a process which we want to just keep it very low priority because it has to run for a longer time, or a batch process, or there are like the processes which are not, because everything has a cost. So when your process is running on the compute the CPU, it is basically generating a cost. Like if you have worked on Amazon AWS EC2 instance, so EC2 instance is basically charging you based on the machine you are opting for, what processor you want, or what operating system you want, what processor with RAM, how much RAM you want. So those are basically the things which are basically making your running an EC2 instance costly. I think the lowest one which you can create on AWS instance is with 2 gigs or 1 gig. So 1 gig RAM is given to you, and in that particular instance, EC2 instance is free for you to actually run anything. So whenever you start creating your account on AWS, they will be giving you 750 hours of instance. So I mean to say, instance is a machine. It could be your Ubuntu machine, it could be any server. So that you can set. I think you should also try whenever you get some time to actually create AWS account and try to use these free 750 hours of one particular instance. So that would become your remote operating system or remote machine which you can interact through terminal. And the way you interact with that is SSH. So using SSH you can log into. Okay, so clouds are basically next generation computing platform. So I would urge if you can start experimenting, because being a student, so AWS, so being a student, they will give you free training, and also there are free credits that you can use for doing and learning so many things over AWS. I think if you are inclined toward using and working on cloud technologies, managing remote servers, hosting web services, such things are of your interest, then you must try on AWS because they gives you free bucks and free compute things, so you can put anything onto their S3 storage. So I don't want to go into detail, but this is good if you can go there. And coming back here, so basically each and every the priorities are there. There may be the funds, those are available, and based on that we want to keep one process low profile, low priority, because it has paid a few bucks only. So something like what I'm saying here, it may be the external priorities which enable and which calculate the priority of scheduling that particular process. I hope so. I just repeat again, priority scheduling, in deciding the priority of a process, we have internal things which are happening within the operating system. Then there may be external impact or criteria which can be used for setting the priorities of the process. And once the priority is assigned, it is very easy to basically create a ready queue from where the dispatcher would actually take the information and then allocate the CPU. Here is some priorities that are already assigned. So here you can see the process P1 has a CPU burst time of 10 milliseconds. Its priority is 3. P2 has the highest priority, whereas P5 has second priority, second highest, then P1, then P3, then P4. So this is the Gantt chart, and how they would be actually executing. So it would depend upon their priorities. So P2 would execute first, then P5, then P1, P3, and P4. So average waiting time for this particular scheduling is 8.2 milliseconds based on these 5 tasks. It could be preemptive and non-preemptive scheduling could be possible. Preemptive scheduling is whenever there is a newly arrived process. When you're now here, this is a static thing. So we have a set of 5 jobs in our queue, and we prioritize them, and then we started assigning it. It means that, let us suppose there is another job which is added, P6 of highest priority, let us of 1. Then what would happen? So there are two chances. One is preemptive priority scheduling. It will preempt the CPU if the priority of newly arrived process is higher than the priority of the currently running process. Now there could be non-preemptive scheduling if the simply put the new process at the head of the ready queue and keep running the lowest priority process onto CPU. But what that would create a starvation problem. So starvation problem is basically when a low priority process may never execute. So that is basically one of the problem with priority scheduling. There is a fun fact that in 1973 at MIT, they shut down their computer and they found that a low priority process that has been submitted in 1967 had not yet been run because of this priority scheduling, and that particular process never gets enough priority to actually get executed. So this was always lying there for so many years and still not executed. What is the solution to this problem is aging. So aging is implemented using increasing the priority of a process by time. Let us suppose there is timer attached to each and every process, and if as the time passes, the priority keeps on increasing for that particular process per second or per unit time. So we assign it, okay, this is how the priority of this process would increase, and based on that, slowly your process would become higher priority process and get executed. This is something solution or patch to the algorithm called priority scheduling. This basically takes away the problem of starvation, which happens with the priority scheduling. Okay, so we can basically combine round robin with priority scheduling. So two algorithms can be attached together in such a way that system execute the highest priority process and run the process those are with same priority using round robin. In case, so what we are doing is we are using two algorithms now. One is priority scheduling and other is round robin scheduling. In priority scheduling, the ready queue is created using priorities. Then the priorities are assigned to each and every process. And then if the two processes has same priority, then they are basically executed using round robin as scheduling. So let's see this example, how this would happen. So here we can see P4 has highest priority with CPU burst time of 7 milliseconds. Because this has highest priority, so it will start executing and CPU would be allocated to it. When I'm saying CPU, I'm considering I have single core, one CPU processor. So next we will be discussing more on to multi-processor system. So here I have only one processor and to which I'm allocating. So process 1 P4 would be allocated first and it will start executing. How much time it will take? It will take 7 milliseconds. After that, the priority 2 is the turn. Now here we can see the process 2 and process 3 has same. Now in that case, what would happen? Now if this is the case, then the round robin scheduling would start. So what it will do with the time quantum of, let us suppose here the time quantum is 2 milliseconds. So the time quantum is 2 milliseconds. So first P2 would be allocated the CPU. After 2 milliseconds, this is 2 millisecond time quantum slab. After this 2 milliseconds start executing. So the burst is for 5. Okay, so we need 3 basically. 2 milliseconds, then 2 milliseconds. For this it is 8. So let's see. So first, because it is 5 milliseconds burst time, so it will take 3 quantums to actually get executed. So P1, P2, 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 it will take 3 quantums, 3 slices to actually get executed. Then we have P3. So at this particular time, now we have only one process which has a priority of 2 and which is P3. So now it has priority 2. There is no other higher priority process. Others are just 3, so it will keep on running. Now from 16 to 20, this is 16 here. From 16 to 20, only P3 is running. Why? Because now it has the highest priority in the queue. Then after that, what would happen is basically P1 would start. Now P1 has the priority of 3, and then P5 has a priority of 3. So P1 would start executing, and so on. This will happen. So this is how the queue would actually be created, and this is how your jobs will be allocated to CPU. Okay, now I just want to show you how we basically look at the priority of a process. Now, if you look here, the priority of process is given by Ni. This is called nice value for that particular process. PR is the process actual what is called priority. So this was the initial priority, and now this is the nice priority, nice value. We call this as a nice value. What is happening? So process, this root, entered into the system with a priority of 20, and over the time it has been reduced to 0. So it means that it has taken more priority. So smaller is better. Any process with negative 20 has a highest priority. Any process which is having positive, that is basically called lowest priority. So it basically changes. So now you can look here, this process entered with the priority of 0, and now its priority is -20. So it actually get elevated. So it's basically the new priority has become the highest priority for this particular algorithm. So this particular top command is showing the priorities of the processes. So similarly, we have another PS command that can assign PID, PPID, and then we have Ni is a nice value, and com is command. Let's see where I'm running it. So now here you can see the PID and the PPID. Now what is PPID? It's a parent process ID. So basically this is the system ID. So the nice value for this is 0. So nice value is the priority, the current value of the process, or the current priority of that particular. So this is called nice value. For Linux, the nice value would be something around always around the priority value would be from 0 to 139, where in which 0 to 99 is for real-time processes, 100 to 139 are for the user processes. So these commands can actually show you that what is the current priority of your, or nice value of your process moving forward. Now next is multi-level queues. We have seen that there are priorities assigned to each and every job. Why not to create multiple multi-level queues rather than having one queue? Because it makes searching and then doing the round robin make it more complex. So rather than having that single queue, we could have multi-level queue where each queue would have some priority. The task in that particular queue would have the priority. So priority 0 means the highest priority task. So task 0, 1, 2, 3, 4 are highest priority tasks, which would be executing first, and within this particular priority queue, it would use round robin algorithm to schedule all these highest priority tasks. So whenever all the tasks in priority queue priority 0 are finished, then the tasks in priority level 1 would actually start executing. Within this, it will use RR algorithm. Is it clear? Okay, Ryan, thank you. So with both priority and round robin scheduling, all processes must be placed in single queue. So rather than, it's better to actually separate them, and this is basically the approach, and this is how we actually use it. Now what happens is, I just want to go here. So in actual operating system or modern operating system, there are classes of jobs, and those classes or jobs are allocated to these multi-level queues, and where you can see that there is a highest priority this priority goes up. So as the priority goes up from this to this, any student process is having lowest priority, batch process having second lowest priority, and the system processes as well as the interactive processes, those are having highest priority for your operating system. And this is how basically different queues are managed, and within that queue, round robin algorithm is used to actually allocate the process to the CPU. So any job in the system process would be executed first, and then once it is free, then any job here would be executed. Now there are two policies. Like one is, we know that within the system process queue, the tasks are executed using round robin. Okay, now what about this the scheduling within the queues? So for that there are two methods. One is a fixed priority. So fixed priority is the highest priority queue would be empty, then the second lowest would start executing. That would also give the starvation. So starvation is the lowest priority process would always keep on waiting for the job to be executed or allocated to the CPU. But the another approach is time sliced. So within these different, we can have time sliced. Let us suppose like here, this example just discusses two queues. One is for foreground interactive processes, another is for background. In that we can share the CPU time in between. So let's suppose 80% for the foreground processes and 20% for the background processes. Now, and another thing is, we could actually change the algorithms here. So the foreground is using round robin to be for executing the task, and the background batch is just executing the first come first serve. Now here we have 4 levels. So it could be round robin, round robin, round robin, and this could be your first come first serve, first come first serve. So it depends upon the type of the class of the processes we are getting in a particular queue, and based on that the best algorithm would be chosen for scheduling those algorithms to the CPU. Till now you might be aware of that not all algorithms are best for every class. So basically, similarly, if you are developing one program, so not every program would be best for every type of data set which is coming. If you remember, we discussed about data parallelism, and we also discussed about the function parallelism. How the data is coming, how to split it, and how to execute the same algorithm cannot be. That's why there are so many algorithms already available in the market, available in the computer science domain, and we have to pick and choose one algorithm approach to actually do it. So you need not to actually implement each and every algorithm. The algorithms are available. You need to wisely choose which algorithm would fit to what type of problem. So that is always the trade-off that happens in computer science. So that's why there are algorithmic complexity is a term which all of you are aware about. We always look for this type of complexity, what is good, which algorithm is good, which algorithm is not good. So time and space are two things that basically there is a trade-off between the algorithms. If time is less, space is more. If space is less, time is more. This trade-off actually we need to calculate and find out what type of algorithm is best suitable for our job. So, and similarly, coming back, analogy is we have to choose on which type of scheduling algorithm is best for us. Like the batch processes, they run long, and the best is first come first serve because it's non-preemptive and just allocating whatever is coming based on the priority, based on how it is basically added into the queue. One level next, we have multi-level. Now we have multi-level feedback queues. The multi-level feedback queues says that the priority of an algorithm could change as it is running. And if it is changing, then it should be put into a different queue rather than continue into a same queue. It should change to lower priority queues or higher priority queues. It should be moved from one one queue to another queue. Let us suppose you are running something, and your process has a critical part also. So whenever there is a critical part of that particular process has to run, it should be moved to the highest priority. So that is possible using multi-level queue scheduling algorithm, which says that process can move between various queues, and aging can be implemented this way. So this is how it implements the aging. If there is a process, a low priority process, and it is waiting for so long, it could be moved up to the higher priority queue so that it can actually execute itself. So basically that is the whole purpose of multi-level feedback queues. But number of parameters are there to be tuned, because this becomes a kind of optimization problem. So what is the optimal number of queues for for multi-level feedback queues? What scheduling algorithm for each queue should be used? Methods to determine when to upgrade the process. So what criteria should be there to upgrade a process or downgrade a process? So this has to be taken care. Method used to determine which queue a process will enter when the process needs a service. So we have to decide on where your process should enter. This is the most general CPU scheduling algorithm. It can be configured to match specific system under the design, like for hardware and with operating system. But this is also the most complex algorithm that we have, because there are so many parameters those we need to, rather than just counting the individual queue level priority. We also need to find out how we have to, based on these parameters, how we have to design this whole multi-level feedback queue. So here is one example. So there is 3-level feedback queue. What is happening is this is Q0, this is Q1, this is Q2, and this is highest priority. So whenever a job is there, it enters into Q0, which is served first come first serve. So this is first come first serve, and then first come first serve along with round robin. So it will get 8 millisecond quantum, 8 millisecond quantum. So if the job which is entered, let us suppose P1 here, is executed within that 8 milliseconds, then it is good. It completed its time. If it does not basically complete, it means that the CPU burst time for P1 is larger than 8 milliseconds. So what it would be done for next, it will be moved to the second queue, Q1, where the quantum size is 16 milliseconds. So if the process would actually execute here, then it is good. Otherwise, it still be large enough. So in that case, it's basically moved to the lowest priority queue, that is Q2. So it's first come first serve basically based. So this is how your process would actually give a non-preemptive execution, and non-preemptive execution could allow this process to execute as long as it wants. So here it is basically when it enters, so it will be RR. So it is RR here. So this is RR only. So when it enters into the Q0, it is based on RR, because RR is also applied on FIFO, whichever is first coming. So based on that, it is basically applying it. So RR is based on FIFO, but time sliced. Okay. So this is RR. So then move to another, and then served as basically, again, round robin based. And the lowest priority queue is first come first served. So based on that, it will actually execute the processes. Okay, so now moving next is thread scheduling. In thread scheduling, we started discussing about in chapter number 4 that the threads, there are 2 types of thread: the user level thread and kernel level thread. Each thread, user level thread are created by user, and kernel level threads are basically managed by the kernel. So user level thread are mapped to the kernel level thread. So if you remember, there are one-to-one, there are one-to-many, and there are many-to-many interaction between the threads. So one one user level thread is converted into one kernel level thread. It may be many user level thread converted into many kernel level threads, or it may be many user level threads converted into one user kernel level thread. So this is called mapping. This is called another mapping. Okay, so when in modern system, so the processes run as threads. If it does not create more threads, it is a single threaded application. Okay, so there would be one user level thread would create one kernel level thread. Okay, so user level threads are managed by thread library, and kernel level is unaware of them. To run CPU, user level threads must ultimately be mapped to associated kernel level threads, and those kernel level threads are called LWP. So if you remember, we see the number of the threads for each process from proc and from top. Those are basically lightweight processes. Those are called lightweight processes inside your kernel. So let us assume two scenarios of mapping. The first scenario, you have two user threads and they are mapped to one LWP, so lightweight process. In case you have two user level threads, here is a user level and it is mapped to one kernel level thread. So there's a user and this is kernel space. Two processes 1 and 2 are mapped to one kernel lightweight process. So this means that let us suppose within your operating system already 3 other processes are running. In that case, actually how many processes would go to that particular queue would be 4. So where 3 others and 1 your, because we created 2 user threads in a user space, but they are mapped to one lightweight process in the kernel space. So how many total processes those have become? 3 plus 1. Your lightweight process would get 1/4 of the total CPU time. So if there are 4 processes. Now another scenario, many to many scenario. 2 user level threads are mapped to 2 lightweight processes. So many to many, okay? Or 1 to 1. So 1 to 1 means one user level thread would create one lightweight process. So 2 user level threads created 2 lightweight processes. Now in that scenario, 2 plus 3 are the number of processes those are executing on my system. So my lightweight process, so single lightweight process would get 1/5 time of the total CPU, and your application, because it created 2 threads, it will get 2/5 of the CPU cycle. Now in the previous case, what was happening? Because single lightweight process which was created for me was getting 1/4, and this 1/4 is divided into 2 user level threads. So each of them, the user level thread would get 1/8 time of the total CPU time. So it might be little complex to understand, but if you could visualize it, what I mean to say is there are 2 level of threads which are available in our system. One are user threads created by user application. Some are kernel level threads. So there are different operating system how they create and map each other. Now for Linux and Windows, one user level thread would be mapped to one kernel level thread. So in that case, the second scenario would work. In other operating system, it may be possible that 2 user level threads are mapped to one kernel level thread. So actual process is kernel process. So kernel process is actually running. Now along with this one kernel level process, the LWP, there are 3 other processes running. So there are 4 processes which are running and they would be sharing one CPU. So how much computation would get? Each would get 1/4. Now this 1/4 would also be given to one LWP, which is shared by 2. So it will become 1/8 of total CPU time for each user level thread. So this is little complex, but yeah, so I hope something you have got. Now LWP is the lightweight processes has process ID, whereas user threads do not. So we have seen this, but lightweight processes, they have PID, process ID. Many to one, many to many model, thread libraries schedule user threads are to run on lightweight processes. So that mapping is happening. Now this mapping is called process contention scope. So let us suppose an operating system mapping is done. user level thread is mapped onto different number of kernel level. In that case, the first thing that has to be done for scheduling is process contention scope. The process contention scope is scheduling, means mapping. How many user level threads would be mapped onto how many lightweight process. And this is basically running all the jobs here. This is user space. An application would send through two user level threads. So T1 and T2. Now there are different types of operating system. One says if there are two threads, it will create two kernel level threads, kernel and user. If there are two threads from user space, it will create two kernel levels. There are others too. Like if there are two from user space, it may be possible there are four kernel levels. Okay. So now what I was talking about, the first scenario, there are two threads from the user space and there is one kernel level thread. Our Linux use this approach. So whenever one user thread is coming, one kernel thread is basically created. But this is an overhead onto the system. Let us suppose your application creates 1,000. So kernel has to create 1,000 threads. So this is one-to-one mapping. This is one-to-one map. Okay. Now this is n to 1. So there are 2 or 3 or 4. They are mapped onto only to one kernel process. So this is actually the kernel process is the one which would actually run it. There is only one process. Okay. This particular thing, the process contention scope thread not only just be allocated to the CPU, but before that, it has to map to a kernel process. Before it actually start execution, it has to map to a kernel thread, and that mapping is called process contention scope. So basically the user space thread is getting mapped into the kernels. Okay. And kernel algorithm or the threads would be actually allocated to the CPU using scheduling, whatever we have. Okay. Because now earlier we were discussing about the processes, now the threads. Okay. So the threads are actually executing. Now in that case, we have this particular thing. Okay, for Linux and Windows, they are creating one user thread is created, equivalent kernel thread is created. So then this process is not available for Linux or Windows because this process contention scope is a process of mapping the user thread to the kernel. It's also a scheduling. Like I have n number of user thread. How many kernel threads would be created out of it? It may be m, it may be 1, it may be 10. So that mapping, that is also mapping, and that is called process contention scope. This comes under that particular scheduling component. Okay. Another is whenever the kernel is ready, now the process is ready here. This would be allocated to actual CPU. Now here the ready queue would be done, and this is called system contentions. Our Linux, Windows performs only system contention scope, and competing among all threads in the system using one-to-one model such as Windows and Linux scheduling threads using SCS. So we have only this process for Linux and Windows. It may be possible for other operating systems. This would be the first step, and then this would be the second step. So the process contention scope first would map user level threads to the kernel threads, and then the system contention scope would actually scheduling the kernel level processes for the CPU. So then there are APIs available, which the POSIX APIs are available, which would actually return you what scope is available on your computer system. So that program we would be actually running, and APIs allow specifying either PCS or CSS during the thread creation process. So we have seen how to create the threads, and based on the threads, we have to initiate which process should be taken next. So if it is a Linux system, then SCS would be started directly for that particular thread. Whereas for any other operating system, where is n to 1 mapping is done, then the first process would be the PCS, and then SCS would be happening. Okay, pre-thread scope schedule the threads using PCS scheduling. So p-thread scope process schedule threads using PCS scheduling. So it will first map and then do the thing. Now pthread scope system, schedule the threads using SCS scheduling. SCS scheduling do not perform any mapping because it's one-to-one. So just directly, allocating the threads to the CPU. So this is how is done, and limited by only Linux and Mac only use a pthread scope system. So this is what they are using for threads to scheduling. Let me just give me 1 minute and open this program and let's see. Oh yeah, so if you can see here is basically the program which creates the threads, and now you can see the number of threads we want to create, then the attribute, this structure is created, and here we are passing initial default attributes for the creation of the threads, and this is the function which would actually get the scope. Like what is the scope? And the scope is either your pthread scope process or pthread scope system. So it basically tries to know about what system it is. So based on that, the scheduling would be performed for that particular. So if the scope is equals to the pthread scope process, printf pthread scope process, else it will print pthread scope system. Okay, so we will run this code and then see, and we can see, because this is a Ubuntu system, so it's basically running pthread scope system. This is used for for Linux and Mac system, pthread scope system, where the SCS scheduling is happening for threads.